Here are some quick notes on orbital angular momentum to accompany Chapter 4 of To Build a Star. Now this may seem a little bit off the beaten path for an astronomy class to be going down into quantum mechanics, but of course one of the interesting things or amazing things about astrophysics is that you get to use all of the sort of core subjects of physics, which is nice. I guess it's fun, and it of course makes it feel like you're putting your education to use, which is always nice. But aside from that, orbital angular momentum, as I'll talk about here, is key to understanding the hydrogen atom and just atoms in general. And of course, stars are mostly hydrogen, so if we can learn more about hydrogen, then that'll go a long way to teaching us more about the star. So hydrogen and any atom, you know that the electronic energy levels are quantized. You can't just have any old energy, and for instance, an atom is in an excited state and it de-excites, it can't emit a photon of just any old energy. Okay, it's discretized. And when you took quantum mechanics, you probably found the eigenvalues and also the eigenfunctions of the hydrogen atom. And you maybe didn't even solve it exactly. I mean, it's one of the few problems that is analytically solvable, but in my opinion, it's still pretty involved and a bit difficult. But there are more fun semi-classical ways where we can kind of guess the result of what the eigenvalues should be. So you'll work through one of these in the homework, but here is a kind of different approach, but still semi-classical. So let's just consider our orbiting electron, the electron orbiting the proton at the center of the hydrogen atom. So it has kinetic energy 1/2 mv squared, and the velocity here is the circumference of the orbit divided by the period of the orbit, so that's 1/2 mv squared. From Kepler's third law, we know that the period squared is proportional to the radius of the orbit cubed. And so in the equation here, we have the period squared in the denominator, and so we can plug in their radius cubed, and you see the scaling is that the energy of our orbit goes something like 1 over the radius. Okay, if we're in an equilibrium orbit, then forces are going to be balanced. So you have the centrifugal force is balanced with the the Coulomb force, and so we can go ahead and just solve this, right? You cancel radius, and what you see here is that you have the mass times velocity squared times the radius, excuse me, is equal to the charge squared. Well, the angular momentum is mass times velocity times radius. So we can multiply by mass times radius and divide by mass times radius, and then we'll move the mass times radius in the denominator over, and we'll get that the angular momentum squared is proportional to the radius of our orbit. So what does that mean? That means that the energy of an orbit is inversely proportional to the angular momentum squared. All right, so our electron, we've been treating it as a particle here, but remember de Broglie taught us, even in the old quantum mechanics, that it's also a wave. And the de Broglie wavelength is equal to Planck's constant divided by the momentum. And we're just using the non-relativistic approximation, so we'll just use m times v for the momentum. So the remember the angular momentum is mass times velocity times radius. So we multiply by radius over radius. And our de Broglie wavelength is Planck's constant times the radius of the orbit divided by the angular momentum. Okay, so if we have a standing wave, right, for standing waves you have an integer number of wavelengths. If it's 1D inside that 1D well, if it's a box, similarly you have still integer number of wavelengths. So that means that the wavelength is going to be an integer multiple of the wavelength is going to be proportional to the circumference of our orbit here. Okay, so then if n times the wavelength is 2 pi r, and we can plug in our result for the wavelength here, so we know that this integer multiple of the de Broglie wavelength is equal to the circumference of the orbit, and you can cancel the radius, bring 2 pi over. Planck's constant becomes the reduced Planck's constant, so just divided by 2 pi. And you see that angular momentum in this approximation here is quantized. And so finally, because the energy of the orbit is proportional to the 1 over angular momentum squared, that means that the energy of the orbit is proportional to 1 over this integer squared, and this is what we call the principal quantum number. And this is what you find empirically through quantum mechanics, and you also find this through a different semi-classical estimate that, again, you'll do in the homework. Okay, so why did these semi-classical methods work so well when we base things on angular momentum being quantized? The basic idea of why angular momentum should work is the following. So your electrostatic potential is spherically symmetric, right? It just depends on the radius. It's inversely proportional to the radius. And so when you rotate the hydrogen atom, that potential doesn't change. We don't care about that. And so Noether's theorem tells us that because you're rotationally symmetric in this scenario, that means angular momentum is conserved. And then the Ehrenfest theorem, what that is that the time average behavior of position and momentum in quantum mechanics follows the classical behaviors. There's an analog that I believe is roughly covered in Griffiths, and you can find it elsewhere on the internet, that the analog of the Ehrenfest theorem tells us that the time average behavior of angular momentum also follows the behavior of classical angular momentum. And this all jives with the correspondence principle that Niels Bohr came up with, that quantum mechanical calculations, they reproduce classical calculations for large quantum numbers. And because in this case, the energy is just proportional to 1 over that principal quantum number squared, when it gets large, nothing really changes. So when that number is large, it should follow the classical laws. And when you scale n down, the equation doesn't change. So therefore, the correspondence principle would also tell us that these semi-classical approaches should work. So that's neat that works out. And just a fun aside about Niels Bohr, if you're ever worried that you're making a lot of mistakes in your research or your homework, keep in mind this great quote that is attributed to him. It's attributed differently over time, so I don't know how accurate it is, but he said that an expert is a person who has found out by their own painful experience all the mistakes that one can make in a very narrow field. Okay, so we have one more role for orbital angular momentum, and that is figuring out the degeneracy of the hydrogen atom energy levels. So when you have a state, you have an energy basically that's described by a principal quantum number n, so you have a level, how many states do you have per level? And in the textbook, you'll note that it's basically just quoted that there's 4n squared, so the principal quantum number squared. So why is that? Well, the 4, is explained in the book. And basically the idea is your hydrogen atom is just 1 proton and 1 electron. These can be spin up or spin down. And so you have 4 combinations to put them together. Okay. And then now we need to think about where the n squared comes from. So again, in quantum mechanics, you probably solved all or part of this, or you saw the solution done, that the eigenfunctions of the hydrogen atom basically are separable, so you have a radial component multiplied by the Legendre polynomials. And these are described by this principal quantum number n. You have the orbital angular momentum, and you have the projection of the angular momentum, basically. And what you find, and it just really pops out of the solution of this problem, that the principal quantum number n is going to be greater, it's an integer, and it's greater than the orbital angular momentum, which is an integer. And the projection here, this m number, it's like a magnetic substate, is what some people call it, this is equal to or less than the orbital angular momentum, and it can be positive and negative, so the absolute value is equal to or less than that. And all of these are greater than or equal to 0. And it may sound unsatisfying that these numbers just kind of pop out of the hydrogen atom solution. They also, principal quantum number comes out of just solving a standing wave in a box, because you have integer multiples of the wavelength for a standing wave. It also comes from the old quantum mechanics if you just presume that momentum is quantized, you will basically find that principal quantum number and orbital angular momentum pop out of that solution as well. So the way we can think about these quantum numbers is, roughly speaking, n tells you the size of the orbital, L, the orbital angular momentum, tells you the shape, and you probably remember these shapes from your chemistry class at some point, and m is more or less the orientation of that shape. So the magnetic quantum number m, that runs from minus L through 0 all the way to L, and so that means you have 2L plus 1 projections, basically, for each orbital angular momentum. So there are 2L plus 1 m's, is what I mean to say in that sentence. Okay, so then for each n, what does that mean? Remember, L can run all the way from 0 up to n minus 1. So if we want to get the total number of states, we have to sum orbital angular momentum is 0 up to n minus 1, and there are 2L plus 1 projections. And so what you see when you plug in the numbers is that you're basically adding up all odd numbers up to 2n minus 1. And there's this interesting proof you can find elsewhere called the odd number theorem. And it's if you add up all the odd numbers that you create up to this 2n minus 1, then that is equal to n squared. So kind of neat. And so what does that mean? That means that finally, we have, for each n, we have n squared, and then we also have these 4 combinations based on the spins. And so your degeneracy for a given level is 4n squared. So you have 4n squared states with an energy that is the Rydberg energy divided by that n squared. And that is it for these quick notes on orbital angular momentum.